So, hello guys, let's quickly talk about momentum. Momentum is a product of mass and the momentum of a body is a product of the mass of the velocity of the mass of the body and the velocity of the body. Now, if a particle is moving in an arbitrary direction, like if a particle is moving in an arbitrary manner, then it must have three components: x, y, and what, and z. So we must have px, py, and what, pz. So if this is not p actually, but it looks like p. If p equals to mv, that means our px equals to what, mvx. Py equals to what, mvy. And pz equals to what, mvz. All together. Now, why am I not saying mxvx, mx, myvy? Why is the x only attached to v and the y and the z? Because mass is constant everywhere. The velocity varies. Velocity might vary due to direction, x, y, and z. Do we get? But mass, even in heaven, my mass on earth is my mass in heaven. In any universe, are we together? Like, mass doesn't change. It is weight that varies at different locations. Why? Because gravity varies at different locations. Yeah, yeah. Even on the same earth, we have gravity to varies due to altitude. Yeah, though it's very negligible at some point. Yeah, due to altitude, gravity varies. Now, not to talk of different universe. So, what am I saying in essence is that your weight in Pluto might be different from your weight on Earth due to gravity in Pluto being different from the gravity on Earth. But your mass in Pluto is your mass in Earth, is your mass in Jupiter, is your mass in Mercury. Even in heaven, mass is the same thing. If mass is considered there, yeah, mass still remain the same thing if it is considered. Now, so that's why I'm not adding. So the mass are constant. So that's why I'm not adding. Do we get that? So PS equals to mvx, py equals to mvy, pz equals to mvz. If the body is moving in an arbitrary direction, so it must have these three components. So that's that for that. Now, law of conservation of momentum. When we say something is conserved, that means you have to think we should have initial, we should have final, because now this is a duster. Okay, this duster was here. Okay, and I change the position like this. I now remove part of the duster. This duster is no longer conserved because it's no longer the same duster that I used to know. It has been torn. Part has been cut away. This thing is not conserved. In fact, see, this was the original duster. It has a black cloth on it, but it's no longer conserved. This one has been removed from it. When we are talking of conservation, that thing is either is the same thing it used to be. If I place the same duster here and I move it here, it's conserved because nothing has changed. But when it was here and it's no longer conserved. Can we see that? So there is what it used to be and now what it is now. So now let's now say, now the law of conservation of momentum states that whenever two or more particles, like, or bodies or objects in an isolated system interact, when they interact together, maybe they interact, they jam, or whatever way they interact, I don't want to know, the total momentum of the system remain constant. Now, in a nutshell, the momentum before interaction, because the total momentum must be constant, even after interaction, it must be equal to this. Do we get? So, sorry, it's P. The total momentum before interaction is equal to total momentum after interaction. Take note of that. So, that's about conservation of momentum. Total momentum before interaction equals to total momentum after interaction. Now, types of collision. We have elastic and what? Inelastic. Now, when we are talking of an elastic collision, momentum is always conserved, whether in any case, whether elastic or inelastic, in any types of collision, momentum is always conserved. So, yeah, momentum alone. So, both momentum and kinetic energy are conserved under elastic. They are both conserved under elastic collision. Both momentum and under inelastic, only momentum is conserved. Only momentum is conserved. Only momentum. Kinetic energy is not. So kinetic energy is not conserved under inelastic. But under elastic, both momentum and Ke are conserved. Inelastic, only Ke is conserved. only momentum is conserved, Ke is not conserved. Now let's talk about Ke not being conserved. Now to you, to a good physicist watching me there, kinetic energy is not conserved. So what happened? Now we are not violating the law of conservation of energy. Do we get? As a whole, the energy of that body, we are not violating that energy is destroyed. Law of conservation of energy state that in an isolated system, energy is neither created nor destroyed, but can be changed from one form to another. The fact that Ke is not conserved, our loss in Ke has been converted to other forms of energy. So we are not violating the law of conservation of energy. What are the forms? If two cars jam together, you will hear something like boom. That boom is sound energy. So part of this gas has been converted to sound energy. In fact, at the point of jamming, that point, if you touch it, you feel there will be heat there. So that's another form of energy, heat energy. So sound energy, heat energy, all those ones, they have received part of this energy. That's why this guy is no longer conserved under an elastic collision, to be precise. But under elastic, is conserved. Under elastic, um, there is nothing like this. We have part of it that is released as heat energy or as sound energy. Take note of that. So our total energy is still, like, it's not lost, it's not destroyed. Just that our part of this kinetic energy is convert to another form. So if we still add everything together, those sound energy, heat energy, if we add it back to the final kinetic energy we obtain, you see that everything will still be equal to the initial kinetic energy. So that's that for that. Now, when we have two masses, let's deal with some cases. Now, I want to prove. You can actually count the formula, but you can choose to prove it. That's what makes you a better physicist. Two masses scattering after collision. Like when you have two masses that collide together and they now scatter. So here, let's say M1, U1, this point of collision, M1, M2. Here we have theta, here we have what? Alpha. M2 is sitting somewhere around there. M2 is at this point of collision. Yeah, take note of that. That's why I'm not writing it. M2 is at rest here. And U2 is 0 because it's at rest. So when this guy is coming, when this guy jam M2, they scattered after collision. M2 go to his way, M1 going to his way. Now, now, because they did not part in a straight line, they part in um in a vector component, in a vector this thing, like they have both directional and magnitude. Are we together? So they part. Well, that's not that shouldn't be even shouldn't be it, because even though it goes in a straight line, there's a direction. But what I'm trying to say is that they have they are parting ways now. It's not it's now something to be resolved, like a resolution of vector, because this guy now do not only have x-axis, it has both y and x-axis, because this is now like an hypotenuse. If you draw something like this, you can convert it to a straight line, you can convert it to a sloping line, which is horizontal, like a vertical or horizontal, because this is slant height, which have both horizontal and vertical component. So when they part way, both of them go in each other way in form of horizontal and vertical component. Now, the next thing we need to do now is that this M1, U1 plus M2, U2, these are the total momentum before collision. Even though this one is 0, but let's just write it. Before collision, this, momentum is mass times velocity. Momentum, mass initial velocity equals to, now, M1, M1. Listen. Now, this is our M1. Are we together? Now, let's close this line. M2 also, let's close this line. Now, we want to check the horizontal component of this M1. The horizontal component of M1, which is this, right? And this line is adjacent to the angle. M1 is hypotenuse. So when you have adjacent hypotenuse, that's what? Cos theta equals to what? Let's call this how can I put it? This is should this be, yeah, this is our velocity now. Yeah, this is our velocity. Take note of that. I'm coming, I'm checking something. No. Okay, let's say this is our M1U1. There's a way I want to write it so that you understand. I can just write my M1V1 cos theta here, but I'm looking for a better way to write it. Oh, sorry. Yeah. After they parted, we have M1 here with with its velocity, final velocity V1. M1 with its final velocity, because it's actually going, since something is coming like this. See, it carries, because here we are not considering mass alone, we are considering it with momentum too, with velocity. So it's momentum coming like this. So the momentum is now splitted in this part and this part. So you still have momentum, but here it's no longer initial velocity, it's now final velocity. So you have your M1 V1 here. So this line, you have your M2 V2 final. Do we get that? Now, these are S component, these are Y component. Now, let's find our S component. X is adjacent to theta. So, cos theta is X over what? Hypotenuse. Do we get? So, if you cross multiply, the S component will give you M1 V1 cos theta. So, that's why we have this guy to be equals to what? M1 V1 cos theta. Plus, if you do this one too, our S component, this will give us what? M2 V2 cos what? Cos alpha. Because the angle here is alpha. Do we get that? Maybe you should go and watch my video on vector, on what I just did here on vector, my vector analysis video, so you won't be confused. So now that's our horizontal component. M1U1 plus M2U2 equals to M1V1 cos theta plus M2V2 cos theta. Now, since there is no motion along the y-axis before collision, there is momentum, rather there is momentum along the x-axis, right? Even though the one here is 0, but let's just put it there. This plus whatever we have here, so we have something like this. But on the y-axis, there is no momentum before collision, so is 0 equals to, for the y-axis, is 0 equals to. Now, let's calculate our component on the y-axis. Y here is opposite. Are we together? So this one now go up, this one comes down. So this will be the arrow, this will be the arrow. That means the y for M1 is in opposite direction with the y for M2. Do we get? But the x-axis, they are both in the same direction. See, arrow, 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 arrow. The x-axis, this go like this, this go like this. So if you put this arrow here on the x-axis, it will look like this. If you put this arrow here on there, it also look like this. That's why we are adding. But on the y-axis, this one go up. So the arrow will be like this. This one go like this. The arrow will be like this on the y-axis. So they are in opposite direction for the y-axis. So for the y-axis, since y is opposite to the angle, this will be what? M1 V1 sine theta, opposite sine, minus, why is it minus? Because the opposite, do we get? M2 V2 sine what? Sine alpha. I hope I'm making sense. Of course I am. I'm making sense. Of course. So now, that's one thing you need to know. So now, for this second one, since this is 0 equals to, let me write it here, 0 equals to M1 V1 sine theta minus M2 V2 sine alpha. Now, if you bring this on to the other side, you have M1 V1 sine alpha equals to what? Sorry, M2 V2 sine alpha equals to what? M1 V1 sine what? Sine theta. Now, let's make sine theta the side of, don't forget this formula. Yeah. Let's make sine theta the surrogate of the formula. So here we have sine theta equals to what? M2V2 sine alpha over what? M1 V1. So at that point, you can look for your theta. And if you get your theta, you can get your alpha. I think so. It depends. Now, that's the formula you first need to keep. And the one that I just claimed. Now we are done with that part. Now, another part. When we have something like this: m1 u1 momentum, m2 u2. This one also has its momentum, and they collide at this point of collision. And after they collide, they still go the way they came. They don't go to the one we did earlier, like slant, all those one. So we still have m1 v1, m2 v2. Now for this one, total momentum before collision, m1 u1 plus m2 u2 equals to what? m1 v1 plus what? m2 v2. This one is still if they scatter, like if they did not stick together, if they scatter after collision, you still have it like this. Do we understand that? Now, this is like our third equation now, or our fourth. Should I call it third or fourth? So I think this should be our third equation. Now, also don't forget, this is when momentum is conserved. Of course, momentum is always conserved. Keep this formula too. Scattering after collision on a straight line. Down the initial one, scattering after collision on a slant direction. Do you get that? Now what of, let me write this one here now. m1 u1 plus what? m2 u2 equals to what? m1 v1 plus what? m2 v2. So now let's also talk about kinetic energy. Are we together? Now what we want to derive now, the formula we want to derive now is what is known as coefficient of restitution. So we want to derive this formula. Now follow me. So we started from this one. This is where we are now. Now for kinetic energy, here now, when kinetic energy is also conserved, we have total kinetic energy before collision 1 over 2 m1 u1 square plus 1 over 2 m2 u2 square. They are not the same mass. Yeah, like these are different masses. Equals to what? 1 over 2 m1 v1 square final plus 1 over 2 m2 v2 square. Do we get that? Now, let's say what should we call this one now? Let's call this guy. I'm trying to number the equation. Okay, this is equation 3. This one is equation 4. This this is for this two is for elastic collision. When momentum is conserved, when kinetic energy is conserved, elastic collision. Now from equation 3, we can deduce that if you make m1, let's gather all the m1 together. From equation 3, we have m1 u1. If this one comes to this side, we have minus m1 v1 equals to m2 v2 minus m2 u2. So this one we have m1 into what? u1 minus v1 equals to m2 into what? v2 minus u2 from equation 3, right? So we are done with equation 3. We have turned it to something else. So here we now have our equation 5. m1 u1 minus v1 equals to m2 v2 minus u2. So this becomes equation 5. Do we get that? So now, from equation 4, which is this, now, this since both everything have half, you can factor out half here and factor out half here and get rid of it. So here now, let's forget about all the half since half is common to everything, so you can neglect it. Do we get to derive another equation now? Here, let's say here we have m1 u1 square plus m2 u2 square equals to m1 v1 plus what? m2 v2 square. So now here we have m1 u1 square, m1 v1 square rather. Bring this to the other side, minus m1 v1 square equals to m2 v2 square. Bring this to the other side, minus what? m2 u2 square. Do we get? So this one becomes m1 into what? u1 square minus what? v1 square equals to what? m2 into what? v2 square minus what? u2 square. So this becomes equation 6. So let's get rid of this. We've made use of it. Equation 6, m1 into u1 square minus what? v1 square equals to what? m2 into what? v2 square minus what? u2 square. This is what? Equation 6. Is that clear? So that's our equation 6. I hope I'm correct. Yeah, equation 5 is derived from equation 3 and equation 6 is derived from equation 4. So now, take a good look at this equation 6. I want to clean it, but I'll first turn. Now, this is different of 2 square. If you have a square minus b square, you know it's same thing as a minus b, a plus b, isn't it? We all know that. So, this equation 6 will now become m1 into u1 minus v1 multiplied by u1 plus v1 equals to m2 into v2 minus u2 multiplied by v2 plus what? u2. This equation 7. Let's clean 6. 6 is gone. We don't need 6 again. So we've turned into equation 7. Now, divide equation 7 by equation 5. Divide equation 7 by equation 5. So what is equation 5? m1 u1 minus v1 m2 v2 minus what? u2. Right? So this cancel this cancel this. So what do we have left? u1 plus v1 equals to what? V. Wait, I'm come. Oh yeah. u1 plus v1 equals to what? v2 plus u2. Yeah, that's correct. So we've gotten equation 8. Equation 8. Can back it and look to what I did. u1 plus v1. There's no even need. u1 plus v1 equals to v2 plus what? u2. Now bring all the u together. So here you have u1 minus u2 equals to v2 minus v1. Now divide them. So here you have, you are going to have something like v2 minus v1 over what? u1 minus u2, which is equal to coefficient of restitution. So we place them over each other, like bring them something like that. So coefficient of restitution, normal for elastic collision is always 1. For elastic collision is 1. Since they are equal, if you divide them, they will be equals to 1. So if you cross multiply again, you get this. So that one is our E for elastic collision. So that's what we want to derive. So now this is the formula. Our E equals to V2 minus V1 over what? U1 minus what? U2, isn't it? Now, when E is equals to 1, that is elastic collision. You should know that. You know we derive this equals to this is from elastic collision when both momentum and kinetic energies are conserved, which we just proved. It means elastic collision. Now when E is not negative but is less than 1, something like, because here we are not getting negative value. Let me say 1, when 1 is greater than E, and not just, 1 is greater than negative number, but E is also greater than 0. Take note of that. So this means inelastic. This one is inelastic. When you have your coefficient of restitution to be in between 1 and 0, that's inelastic. When it's equal to 1, that is elastic. Please take note of that. Are we together? But when your E is equals to 0, that is coalition. Coalition rather. What do we mean by coalition? When they say you and somebody coalesce together, that is you combine idea together, you come together, like when the bodies stick together. Are we together? When the bodies stick together. So we are going to have something like this. Coalition. It means sticking together. Inelastic, elastic, coalition. Now, and don't forget, we can prove it actually. But because of our time, we can have our change in kinetic energy to be equals to 1 over 2 m1 m2 over m1 plus m2 multiplied by u1 minus u2 into square into 1 minus what? E square. So this is known as change in kinetic energy. Please take note of that. But I will also show us another way in case you cannot cram this. Am I communicating? Now, but note, if our change in kinetic energy equals to 0, then E equals to 1. When coefficient of resolution is 1, then what is change in kinetic energy? 0. Even though if they give for elastic collision, please take note of those conditions. For elastic collision, let me not forget that. For elastic collision, are we together? So now, that's that for that. But let me give us another formula for loss in kinetic energy. Okay. I'm coming. Change in kinetic energy. This one is for now to find your change because this formula, I'm trying to check something. Yeah, if we are dealing with elastic collision, all these things we have here will be equals to 0. Yes, if you are dealing with elastic, it will be equals to 0. But if this guy is less than 1, greater than 0, we will not get 0 here. That is inelastic. And if you don't remember this formula, if it is elastic, you don't need to be calculating your change in kinetic energy. If it's elastic, you always know it's equals to 0. But if it's inelastic, you can also use the formula because they will give you this guy to be less than 1. But if they don't even give you can use this formula. 1 over 2 m1 u1 square plus 1 over 2 m2 u2 square equals to 1 over 2 m1 v1 square plus 1 over 2 m2 v2 square. You can use this, and if this guy is smaller than this, then you find this. When you add this two together, you add this one. If this one is smaller than this, you subtract it to get your change in kinetic energy. To get your loss in kinetic energy? Do you get that? So you can do it this way. And so this is just it. Loss in kinetic energy or change in kinetic energy equals to kinetic energy after no, the one I wrote earlier, they are not equal. For them to have loss, they are not equal. But for inelastic, they are not equal. But I just use the elastic formula to show you that this equals to this. Then find this and find this, subtract them. It's Ke after collision minus Ke before collision. So you can just use this one instead of this in case you don't remember this. But if it is elastic collision, it's stated as elastic. You don't even need to find this. This is always equals to 0 for elastic collision. Take note of that. Now, what of when objects stick together after collision? You have the formula to be m1u1 plus what? m2u2 equals to what? m1 plus m2 into v. Now they have stick together, so they don't have a separate mass. If you add these two together, it becomes a single mass. So they now have mutual a common velocity. There is no velocity for m1, no one for m2 because the two masses have been stick together. So they move with the same velocity. They are not joined together. So this formula is for when if they don't stick together, you still have m1 v1 plus m2 v2 on this side. But when they stick together, it's on this side. Take note of that. Now, let's solve some questions. So please take note of what and try to subscribe to my channel membership. It's the least price you can ever see, just 1,000 naira per month. Tutor there, we give assignments. You can just click on the join button, then just subscribe. Just 1,000 naira per month using your bank card. Thank you very much. Now let's solve a few questions. I'm coming. Let me go and pick my notes. I don't have time to be writing the question. Like I have to rush somewhere. So let me go and pick my notes. Thank you. Thank you. Oh, I did not pause the video, Seth. Sorry. I went to pick my notes. So, though I should have paused the video and write the question then, but it's not even the video. I have somewhere to go. So, let me just be reading it from my notes. So, an object of mass 3 kg, an object of mass 3 kg let me. So the question says, yeah, an object of mass 3 kg, m equals to 3 kg, moving with an initial velocity of u equals to 5.0 I meter per second, collide collide with and stick to an object of mass, this m1, this u1. I don't want to put one before because I'm thinking we are only given one mass. So collide and stick to an object of mass 2 kg, m2 equals to 2 kg, with an initial velocity of u2 equals to minus 3.0 j meter per second. That this is in negative y-axis j. They are giving you in vector form. Find the final velocity of the composite object. Find v. An object of mass with an initial velocity of this, collide this and stick. And stick, you can see the word stick. If they say separate, there's a way the question will be asked. They won't ask you to find common velocity, because if they don't stick together, they won't have, each of them will have their various final velocity. So the fact that they mention stick, so they will have the same velocity after collision. So now we have m1, which is, don't forget the formula, m1u1 plus m2u2 equals to what? m1 plus m2 into what? Into v. What's our m1? 3. What's our u1? 5i. Yeah, don't eat the I. Yeah, because your answer must be in vector, because the initial velocity are in vector form. This must also be in vector form. Plus m2 minus 3j equals to what? m1 plus m2, 3 plus 2 into what? V. So this one give us 3 times 5i. We have what? 15i. Plus times minus, that's minus. 2 times 3j, 6j, equals to 3 plus 2, 5v. Now if you divide, now v will give you what? V will give you 15i minus 6j over 5, right? And that gives you what? That's 15i over 5, which is 3i, minus 6j over 5, that's 1.2j meter per second. So our v is 3i minus 1.2j meter per second. Please take note of that. Now the last question here before I call it off. The last question here before I call it off. So yeah, I'm having a 3 kg particle. A 3 kg particle, mass equals to 3 kg, has a velocity of 3i. Velocity equals to 3i minus 3.0i. It's still 3i, no problem. 3 point, but some people they make mistake and make it 30. That's why I want to add the 0.0 meter per second. They make this one 40. They are not calm to watch, to look at question as a good physicist. I don't know what's wrong with them. Find this x and y component of momentum. Find this x and y. This is the x component. I is x, j is y. So, and you know momentum p. If there's any place, okay, I think there's no place I represented momentum with here. Momentum is, it looks like p but not p. I think it's called rho. Momentum is mv. I told you, whether on the x-axis or on the j-axis, the mass is the same, except if they are talking about two bodies. Once it's the same body, this mass, the mass on this component is the same thing as the mass here. Mass is same thing everywhere. So we still use the 3. Let's say vi, momentum on the I component. So what's our I component? Times 3 equals to what? 9i. So momentum on the j component equals mvj, equals 3 times what? Minus 4. That's or minus 12 what? J. So our momentum now, this is the momentum on the I component, this is the momentum on the j component. So we can now say that our momentum equals to what? 9I minus what? 12J. Kg meter per second. Yeah. Am I right? Yeah. Kg meter per second. Take note of that. Now, another question at the part B of this last question say find the magnitude and direction of the momentum. Magnitude and direction. If you have watched my video on vector, you know that the magnitude and direction theta equals the tan inverse. Don't forget the y component coefficient minus 12 over the x component coefficient over 9. Yeah, if you find this, I think this give us, I'm not sure, my calculator is not here. I think it give us 50 something. Let me just say 53 degree, 53.4 degree. Yeah, our theta is 50 something. If you type minus 12 over 9 and you find the tan inverse, you are going to get something like this. Whether it's 53 or 50 something, whatever it is, that's not my point. Punch your calculator and get that answer there. I'm sorry, there's no calculator for me today. So now, what I want to show you that on which axis do we have this? Don't forget, this is our momentum, 9I minus 12J. Now let's draw the axis, quadrant rather. The first quadrant, everything is positive, right? All is positive, do you remember? The second quadrant, x and y is positive, x is negative. The third quadrant, y is negative, x is negative. Here our x is positive, y is negative. So x is I, y is j. On the fourth quadrant, x is positive, y is negative. So our y, j is negative, which is why x is positive. So this angle is on the fourth quadrant to the x-axis. So you can write this theta. Your angle now equals to, you don't need this negative again, since you found the quadrant, equals to 53.4 degree on the fourth quadrant to the x-axis. Yeah, always take it to the x-axis. So thanks for watching. Don't forget to like and subscribe and share the video among your friends. Please always drop your comment on the comment section. Thank you. And my channel membership is just 1K per month. I would love you to be part of it. Tell your friends. It's just 1K per month. Probably the cheapest among all. I don't know, but it's the least price. Thanks for watching. I love you.